So today I'm going to start the Maxwell equations. So here I will discuss the concept of displacement current. It's a very interesting concept. So first of all, let us recall laws containing, as all of you are familiar with those laws. So let us recall laws containing divergence and curl of electric and magnetic fields. So first law is the del dot E. We take the divergence of electric field, then it gives us the rho over epsilon naught. Rho is the charge density, and this is known as Gauss's law. Let us call it as equation number 1. And if we take divergence of magnetic field, then it comes out to be 0. And in general, this law has no name, and in some books people call it as Gauss's law in magnetism. In some books people call it as, and let us call it as equation number 2. Then if we take curl of electric field, then it is equal to minus curly B over curly T, rate of change of magnetic field, and this is known as Faraday's law, right? Then del cross B is equal to mu naught J, and this is known as Ampere's law, right? And these all are the differential forms. Right. So, and equations. These 4 equations represent the state of electromagnetic theory, before Maxwell, right? But these equations has some inconsistency. These equations have, or you can say that there is a fatal inconsistency with these formulae. What was that inconsistency? Let us have a look at that. Since we know that, as you have studied in the beginning of electricity and magnetism, that divergence of curl of a vector field or vector is always 0, right? So keeping this fact in mind, and we will take the divergence of equation 3 and 4, right? So let us take the divergence of equation 3. Means we will take now the divergence of equation number 3. So if we take divergence, then this equation number 3 can be written as del dot del cross E is equal to del minus curly B over curly T, and this equation can be further written as minus curly over curly T del dot B Since if I use equation number 2, then this is again 0. So that means if I consider divergence of a curl, then this is 0 and this is again 0. So that means left hand side and right hand side both are 0. But what happens to this equation number 4? So if I take divergence of both sides of equation number 4, means let us take equation number 4. So if I consider equation number 4, then I can write down it as del dot del cross P. It must be equal to del dot mu naught J, right? And this can be written as del dot J. Now let us see what will happen. Left hand side is the divergence of curl of B at its 0, but for steady currents, this del dot J is equal to 0. This is from the equation of continuity. Means del dot J plus curly rho by curly T is equal to 0, and rho is constant for steady currents, right? So that means this is, so what does it mean? It means that this del dot J will be 0 for steady currents, right? This del dot J, it will be 0 for steady currents. But if current is not steady, that means in such a situation del dot J is not equal to 0. So that means the left hand side is always 0, but right hand side need not necessarily 0 always. Right hand side is not always 0 for non-steady currents. So this is the problem with this equation. So to understand this more closely, let us take an example. So consider an example and here I am considering the charging of a capacitor. So I am having a capacitor and it is connected to battery like this. So that means current is flowing in this way and it is coming out, right? This is the direction of current, and this is the capacitor. So this has a positive plate, this is the negative plate of the capacitor. So this is the example of charging of a capacitor which I am considering now. And let us recall Ampere's law. Or simply sometimes in some books people call it as Ampere circular law, right? So, and I am considering its integral form. It is closed line integral of magnetic field is always mu naught times the current threading through it. There are two different ways to look at this law. So two ways to look at this law. So one thing is that magnetic field created by an electric current is proportional to the electric current and constant of proportionality is permeability of free space. This is one way to look at this law. And another thing is that to look at this law, say it is a current I is flowing through a conductor. So that means if I consider a loop, let's say imaginary loop circling wire, containing current, in which this is a loop, right? So it is a dl distance, and because of this there is a magnetic field. So the line integral, second way to look at it, the line integral of magnetic field B around a closed path in vacuum is equal to mu naught times the total current I passing through the surface, circuit, or passing through it, right? So that is the second way to look at it. So these are the two different ways to look at this law. Now what do? We consider charging of a capacitor. Say this is a capacitor, right? So this is the positive plate, say this is the negative plate, and say IC is the current passing through this, and then it emerged out from this second plate, right? So consider charging of a capacitor. And conducting wire bring current IC onto one plate, so IC current is through it and away from the other, from the other. As the charge increases, as the charge on the plate increases, means when IC current gets charged, then this flows through from one plate to the another plate. That's what we will assume, right? So if I apply the Ampere's law here, and we will assume that there is in the near end there is a loop, right? So let me do one thing. Yeah, DL is there and say IC current is there. So that means if I apply Ampere's law, then closed line integral of magnetic field is equal to mu naught times I, or I can write down it as, because current I is IC, so it is mu naught times IC, right? But if I consider a region inside here, if I consider this region, then means if I consider the region between the plates, and since no current passes the plate, means no current will be here inside the plates, between the plates. That is, charge stops on the capacitor plate. And charge stays here. It cannot flow from this end to this end. Charge cannot move from. But this negative charge is because of the induction. This will be induced here, right? So that means for this inside region, in this region, the magnetic field, its line integral, it will be equal to mu naught times I, but no current is inside it, that's why it will be 0. Thus we are arriving at the conclusion that this leads to arrive at the conclusion that current is discontinuous. Means inside the plates of the capacitor, the current is discontinuous, or there is a discontinuity. So thus there is a problem with this. So to answer this ambiguity, Maxwell proposed a new idea. Maxwell proposed an idea, and let us have a look at that. What is that idea? This is IC current is passing through it, and say this is a capacitor having a positive charge here and the negative charge here, and because of this is the direction of the electric field inside it, and then current IC will be coming out here. So let us go back to the capacitor. Since instantaneous charge on the capacitor is given as the instantaneous charge on the capacitor is given as Q is equal to C delta V, and delta V is the instantaneous potential difference. And as capacitor charges, electric field between the plate is changing, and since we know that capacitance is equal to epsilon naught A by D, here A is the area of the plate. This is a plate, right? This is the area of cross section, and this is the separation between the plates, right? So A is the area of cross section of the plate. Now delta V is equal to potential electric field because of that and the separation, so ED, and therefore Q is equal to C delta V, and the value of C will be epsilon naught A upon D, and the value of this delta V is equal to ED, and this will cancel out with it. So therefore this charge stored on it can be written as epsilon naught A dot E, or E dot A. Right, but what is it? This is the electric flux, E dot A, because A is the area element, so it is phi E. So I can write down this is equal to epsilon naught phi E. This is the charge. So what Maxwell assumed, he proposed that current inside the plate is not discontinuous, but inside the plate the current is due to change in phi E, because dq upon dt, it is the value of the current, and this is nothing but d phi E over dt, d phi E upon dt, right? And the current inside the plate, Maxwell called this as displacement current. So therefore let us call it as id is equal to dq upon dt, which is equal to d upon dt epsilon naught phi E, and it can be written as epsilon naught can be taken outside, d phi E upon this one. This is the displacement current. So the concept of thus the discontinuity in current, thus discontinuity in current can be now explained by introducing the concept of displacement current. Such that net conduction current such that net conduction current into the volume is equal to the net displacement current out of volume. Means the current IC and here the current ID both are equal, so that this discontinuity will be maintained. So therefore total current or I total can be written as IC plus ID. And if I use this concept, then Ampere's law can be written as this B dot dl is equal to mu naught times I total, and it can be written as mu naught times IC plus ID, or you can say it is mu naught times IC plus mu naught epsilon naught d phi E over dt, right? And in terms of current density, this equation can be written as, or in other words we can say that the differential form can be written as that is del cross B is equal to mu naught J plus mu naught epsilon naught curly E by curly T, and this is the modified form of Ampere's law. This is the modified form of Ampere's law. And this is also known as Maxwell's fourth equation. And here JD can be written as epsilon naught curly E by curly T. This is the current density corresponding to displacement current, right? So this is the idea of the displacement current, and that's all for this lecture. In the next lecture I will talk about 4 Maxwell's equations.